They moved
because
it
I'm
again?
sharing this. No, it moves, but it depends upon where I'm sharing the screen or not. Okay, so in your project folder in BB Learn, there is this little file right here. It says setting up a remote connection to NAU. This is specifically for people who are trying to launch Mentor Graphics, and it was written by Pete like a week ago. So it should be fairly current. This is how you create a project in Mentor. One of the first things you're going to have to do once you get into the Pixis Project Navigator is to create a project. This was updated by me about a week ago, so it's current because all the rules have changed. Your tutorial, which is your guidebook, was written by Sean well, first by Dr. Brower and then updated last semester by Sean Robbins.
Frantically.
When it says things like create a library and you have no idea how to create a library, I would open the Pixis tutorial and Control F to library. And there will be directions. This is the actual project, and I really, you really should go in there this week. I know it's not due for 2 weeks, and at least try to open up the Pixis Project Navigator. If you're having trouble with the getting into Mentor or anything like that, I may have to get Pete involved, and that can take like up to like a day or two. Particularly, there is, each person has their own unique team. It's in this little project one thing. It will be your team for the entire semester. If you join the class late, you're not in here. So Nolan, send me an email and tell me I need to get a team number, and I will get all that set up. It'll take me about an hour or two with whatchamacallit. I got to get Pete involved. Where else? So it's right here. You go to the project directory. You're going to make a directory called project. CD to the project. This doesn't work anymore. You don't have to do don't complain to me about the MGCWD. May or may not work. It doesn't matter. If you type it in, no, it won't hurt you. PPN is what starts the project navigator. It says and then first step says create a project called Project 1. And I would go back and look at that file I just told you about. And then create a library. I would look at the Pixis tutorial for the rest of this. Fairly simple. You need to create a few schematics. Be careful, and I will check them to make sure. You don't have to simulate them until project 2. So, but you'll need to get all the errors out before you simulate it. So I'll try to help you with that. Let's make this smaller and get this out of the way. Not that
I've got a quick question about
yes.
part 7. What is an equilibration circuit? I don't know what I'm supposed to be doing here.
Yeah, you're right. And you will see the equilibration circuit for the first time today in the slides. It's also
that makes
in
sense.
chapter 2 of the DRAM book.
Okay, that makes sense.
It's three transistors. It's not a big, horrible circuit.
It's not something that'll scare us.
It's not something that'll scare you. You have to make one schematic that has a transistor and a capacitor and some output ports and that kind of thing. You need to make one transistor that has one schematic that has 3 transistors in it. And then you need to create an upper level schematic that has 4 of your 1T, 1C cells in it. And do it hierarchically. Okay, pre-lecture 3 was due today. Homework 1 was due today. We have pre-lectures, pre-lecture, pre-lecture. And 2 weeks from today, project 1 is due. And then the following week, you get homework 2. Okay, so this is a relatively new slide by last year or 2. I think I stole it from Dr. Cambeau or Daniel Eichenberger. I can't remember which. This is the way they're building DRAM cells now. And this is kind of an upside down view over here. Where's my pencil? Hopefully it works today. Yay. Okay, so you got the word lines here. Though the word lines are, remember, the gate of the 1T transistor. On the other side, in between the word lines, I have the digit line contact. There's one right here. It's a via that's going right through. That one's labeled. And on the other side of the digit line contact, I have these capacitors. And notice those capacitors are buried into the substrate. They're long, they're thin. Let's look at a few things on here. I want to change my pen color. To something light. No, not gray. Here, white and sparkly. So right here, notice that there is a little bump. This is a defect. It's not big enough to short between capacitors, but it doesn't take a lot of imagination to think that there's going to be places where those bumps are going to be a little bit bigger, and I'm going to short out the capacitors. So burying the capacitors like this deep into the substrate, I have issues with shorting. Another thing too is there's a parasitic capacitor between the capacitors because they're running parallel for so long next to each other. There's crosstalk between adjacent cells. The way this thing looks schematically is, let me make, oh yeah, I can do that. The way this thing looks schematically right here is I've got the capacitor, and see it's buried in the substrate. In between there, there is a layer, a conductive layer. Oh, no, I don't want to get out of the shiny thingy. There's a conductive layer, the titanium nitride. There is a high dielectric coefficient laminate, and then there's another layer of conductive titanium nitride. So all the way along this finger right here and the next finger is the capacitor to make the area larger, to make the capacitance larger. Okay, yield issues, putting them too close together, getting those bumps in there, yield issues, getting them, getting them shorted out, crosstalk, definite crosstalk issues. Especially as the transistor sizes get smaller, which means the area between the capacitors gets smaller and smaller and smaller. Okay, this is where we're at in the last year or so.
Is that where the complex twist starts to come into play, where since it's getting more complex, you can actually start, well, make it more complex even though it's getting smaller and smaller?
We'll talk about twisting later on today. That has to do with signal integrity, okay? And that is on the digit lines. I'm going to twist the digit lines from one layer to the next to get the signal to noise ratio up. I'll go through that in lots of detail. That might have been on your pre-lecture quiz, is why I'm getting good questions. Alrighty, okay. So chapter 2, which is what we'll be covering over this week, focuses on the array. We're going to look at the individual n-bit cell, the 1T, 1C, in a lot of detail. We're going to look at the sense amps in a lot of detail today, or relative detail. We won't do everything. And the word line driver and the row decoder we'll get to next class. The later classes, we're going to talk about the column decoder, how you actually do that decode circuit we've talked about, how the data moves through the memory, what the address path looks like, and how I get voltages like VCCP and VDD over 2 that I've already seen that I'm going to need inside this device. Okay. Now for the cell options, the first thing that they did, what's the word? They did the open digit line. It had problems, and let me just go through this. It had some problems. And the folded has problems too. And I'm sure they've gone beyond that. But once you look at 3 or 4 of these, when you see what they're doing in the real world at your particular point in time, you'll understand what kind of thing they're doing. And the next thing we want to talk about is the different types of capacitors. Remember, back in the old days, we had the luxury of the gate transistor being big enough. The transistor, the gate, one of the transistors in the unit cell having a large enough gate that was the capacitance. Well, we can't do that anymore. We have to go to increasingly more complex versions of capacitors. Okay, this is the open digit line. We've got the row going in this direction. So this is the word line, the row driver right here. It's driving a whole bunch of columns inside that array. And the digit line, likewise, where's the digit line? Digit line's going across here. It's driving a whole bunch of digit lines in the array. I turn on one word line, one digit line, and then that data goes to the input of the sensing. Okay, let's go ahead and start talking about the problem with this. The way this is laid out, I've got the sense amp in the column pitch. So it can only be as wide as one column because I've got to put another one right next to it. So the column is, 20 nanometers. My sense amp's got to fit 20 nanometers by however long I have to make it. Now with this amplifier, we're doing a comparison. It's really acting as a comparator. And what I'm comparing here is I'm comparing the digit line from one part of the array over here to the digit line in another part of the array over here. Now, when you think about this from like a fields perspective and a pickup perspective, the radiation that you see on this side is going to be slightly different from the radiation you see on this side. So the noise picked up over here is going to be a little bit different. The noise pickup from over here, and yet we're comparing these two. Because of this, we have a problem with something called signal to noise ratio. This isn't exactly VCC over 2 as this half of the array sees it. So there's some things that may be a 1 that may not trip as a 1, and there's some things that are a 0 that may not trip as a 0. That's the problem with this. Now the big advantage of this, if we look at the cell, here's a blow up of the cell right here. Can I zoom in? Yes, I can. I can zoom in with my fingers, wow, but I can't move over.
Power of Zoom in Zoom.
We're zooming in Zoom. Okay, so we zoomed in right here. And I did it with my fingers too. It was amazing. Okay, sorry. Get so excited over the little things. So here's a zoom in of the n-bit cell. And when I talk about an F is a feature size. And generally for most processes, there's a minimum feature, well, for all processes, there's a minimum feature size. And every time I put something in, the minimum size for that is the minimum feature size for the device. So like this word line here, the smallest width I can make. Oh no.
Did you freeze again?
I'm frozen.
All right.
I'll see you in about 30 seconds.